Okay, let's start going over this homework. So homework 9, it's assigned today. It's due on the 18th. It's a simple homework. We'll just try to, remember some of the old ideas we've touched on before and apply them in a bit more details today. And yeah, let's go. So problem number 1, please read the examples from your 11 spiel. The chapter is posted week number 12. They're good examples. You don't have to submit anything for this problem. I'm missing a T here, right? You do not have to submit anything for this problem. Yeah, just read the examples. Okay, problem number 2. Let's have a look at this problem. It's problem 10.9 from Levenspiel. And in this problem, I have a homogeneous catalytic reaction, which A plus B goes to 2B. My reaction rate is KCACB with a reaction rate constant equal to 0.4 liter per mole per minute. And for the following feed and reactor spacetimes, we're told the flow rate is volumetric flow rate 100 liters per minute. Your feed composition is 0.45 moles per liter of CNO, CBNO 0.55 moles per liter. Your spacetime is 1 minute. And you're being asked to maximize the concentration of B in the product stream and used a simulator, and the simulator told you this is the best approach, where I use a PFR with 100 liters and I'm recycling, and I have a recycle stream which is an extensive recycle stream, right? 7.85 liters per minute. So do you think that this is the best way to run the reactor, or run this reaction? If it's not, suggest a better scheme, and you don't need to calculate any of the reactors. I just qualitatively gauge if this is the best reactor or not. And when approaching these types of problems, again, we've touched on this a few times before. However, when approaching these types of problems, you always want to get your minus 1 over RA versus CH. So this is problem number 2. You're given a reaction which basically goes A plus, is it A plus, have a look here. A plus B goes to 2B, right? So this is somewhat of an autocatalytic reaction, and the proposed scheme is to operate it this way with a PF4, right? And this is PF4, and you're given some kinetics, so you're being told that the reaction rate for the system is KCACB, and K is 0.4 liters per mole, right? So you're being told that minus RA is equal to K CA CB, and that K is equal to 0.4. Okay, so how do we gauge this? And again, when you're being asked to see if this is the best reactor or not, you should always try to get a plot of minus 1 over RA versus CA. And we've touched on this a few times throughout this course. However, this is what you need to do to gauge if this is your best performance or not. And one thing you need to know, for this type of system, so if I have a bimolecular system, because CA plus CB is equal to 1, so in this case, I'm being told that CA, concentration of A over concentration of B is equal to 1. So if you have a look at your feed, CA note is 0.45 and CB note is 0.55, right? Sorry, CA note 0.45, CB note is equal to 0.55. So if you do a mass balance, this will always hold, right? CA plus CB will be equal to 1. So for this type of scenario, if you plot your reaction rate, which is basically R A versus CA, you're gonna get a maximum. You're gonna get a curve which looks like this. You can verify this if you want, and the maximum will occur at CA equals 0.5, right? This is the maximum rate, and as your reaction progresses, your Ca is going to decrease. So this is the progress of reaction. This is how this reaction progresses. And this is really the chart of reaction rate versus Ca. And your feed, so if we said that this is 0.5, your feed is somewhere here, which is 0.45. So now if you translate this into a -1 over RA versus Ca chart, so I have -1 over RA versus Ca, and this is the chart that will really give you a gauge of how feasible the system is, right? So if I plug this, if I convert this from here to here, I'm gonna get basically the inverse of this curve, right? So I should get a chart which looks like this. And you have to remember that for a CSTR, we talked about this before, if you want to, for a CSTR, the performance or the residence time of the system will basically be just using your Ca note, using your final Ca. So this is CAF here. So for a CSTR, you just draw a box, and the area under this box is the tau for a CSTR, right? This is the tau, which basically translates to a volume of a CSTR. Okay, on the other hand, let's do the same chart. Let's plot the same chart. And let's try to recall how it behaves for a PFR. So I have -1 over RA versus Ca. And we said this is the chart we're looking at. So for a PFR, this chart behaves, or to determine the residence time of a PFR, I need to actually integrate. So for a PFR, I'm integrating. So this is Ca note, we said it. I have Ca note equals 0.45. For a PFR, the residence time is actually the integral or the area under this chart right here, and this will be the tau for a PFR, which translates to a volume of a PFR. Okay, so if I take a look at these two cases, and again, the idea here is, just this is sort of part of the lecture as well, where if you want to gauge whether the performance of PFR or whether reaction should be done in a PFR or a CSTR, you need to plot -1 over RA versus Ca. And for almost all reactions, or for most of the reactions we're going to deal with in this course, it's going to look like an inverse curve like this. And for a CSTR, your residence time, which corresponds to the volume of a CSTR, is basically the square starting from Ca note to CAF, or rectangle, sorry. And this area of this rectangle corresponds to your residence time and your volume. Whereas for a PFR, the area under the curve corresponds to a PFR, corresponds to the residence time of PFR, which is a volume of, which also corresponds to a volume of a PFR. And another thing you need to remember, which we've also talked about this, is that as you increase your recycle, the volume of a PFR is going to approach that of a CSTR, right? So this is the second thing you need to remember when thinking about these problems, right? Is that, I have a PFR here, and I have a recycle. As the recycle approaches infinity, the PFR performance will approach or will be a CSTR, right? So you can really use these two charts to try and gauge the volume, or which system is gonna give you the performance you want at the lower volume. And then you can also get a judgment whether to use a CSTR or to use a PFR with a recycle. We're just having a look or comparing the values of this rectangle versus the area under the chart. So now if I have a look at these two charts right here, it's obvious that the PFR can achieve this from Ca note to CAF. So this is CAF here, and this is CAF here. It's obvious that the PFR can achieve this reaction at a significantly lower volume, right? a bit less than half or a bit more than half, sorry. For in a much smaller PFR, I can achieve the same progress of reaction. So since this is the case, and then PFR is recommended, so you need to say, okay, I'm recommending a PFR for this system, and as well, there should not be any recycle, right? No recycle, so the recommendation given by the simulation is not valid. It's just simple, so you always take it back to the basics. The computer is telling you, oh, you need to recycle a lot. However, if I take a look here, I can achieve what I want with a PFR without any recycle compared to a CSTR. If I have a recycle, then my performance approaches this chart right here for a CSTR, but I can achieve it in a PFR, so it's fine. So I don't need a recycle. Okay, so in what cases would you need a? So this is the answer to this problem. You recommend a PFR and you don't need a recycle. Okay, so let's move on. Just talk a bit more. So in what case would you want to use a PFR with a recycle? So let's say I have the same exact reaction, same exact system, but now my initial concentration is not, so we said this is minus 1 over RA, and this is CA, right? And we said the minimum or the maximum was CA equals 0.5, and your feed is actually entering at, your feed is at 0.45. This is CA note, and this is CA max. This is absolute maximum, or the max or the minimum of this curve, the maximum of the reaction rate. So at this point, you have the maximum reaction rate, and this is your feed. And in our case, our reaction is moving in this direction, right? So I'm only looking at this area under. What if my CA note? What if I have a case where my CA note is actually, CA note, let's say it's 0.8. So in this case, if I have a look here, CA note to CAF. Okay, I'm comparing, which two systems am I comparing now? So for the case where I have CA note 0.8, I'm comparing the area under the chart from here all the way to here. And I'm comparing this, so this will be the PFR. And I'm comparing this to the CSTR performance, which we said, which will just be this rectangle right here. And if I compare these two systems, in this case, the CSTR will have a lower volume than a PFR, right? Because the area under this rectangle, I just take CA note, sorry, CA has to stop here. If I just take CA note, actually, let's draw this properly. It's a mess now. So here I'm talking about a theoretical case where my CA note is higher than my CA at the maximum reaction rate. So let's say your CA note is equal to 0.8. And let's draw it again for comparing a CSTR and a PFR. Okay, so for a PFR in this scenario, and this is CAF, the residence time of a PFR is going to be this entire volume, and this is for a PFR, whereas for a CSTR, your residence time will actually be only taking this point, and this is my CAF, and I'm going to take this point, draw a horizontal line, and just take this area under the square. And as you can see, for a CSTR, the reactor volume is much less than a PFR. So in this case, I can say, okay, I can use a CSTR or I can use a PFR with a recycle. And in this case, maybe this scenario is valid where I have a recycle. However, in the case given, because I'm starting at a concentration which is less than the maximum reaction rate concentration, then a PFR will always perform better than a CSTR. Try to think about these scenarios, and if you're having a hard time seeing them, please come to office hours and we can talk about it in more details. But yeah, basically try to understand how we can utilize the minus 1 over RA versus CA plot to make a decision on the type of reactor you're using. All right, let me clear this and let's go to the next problem. So for the next problem, we have a look. Yeah, for the next problem, you're being told for a homogeneous reaction, for the homogeneous catalytic system, A plus B goes to B plus B, same thing, minus RA is K, CA, CB, and with a feed of CA naught equals 90, CB naught equals 10, we want about 44% conversion of reactant A. What flow reactor or combination of flow reactors is best that it gives the smallest total volume of reactors needed? And again, you don't need to draw anything or do it. Okay, so this is very similar to the previous problem where I have this system of reactions, A plus B goes to 2B. I have this reaction rate and I'm given CA naught and CB naught 90 equals 10. Okay, let's go back to the whiteboard and this will be problem 3, right? Just write 2 here. And here I'm told A plus B goes to 2B. I have minus RA is equal to K, CA, CB. I'm told that CA naught is equal to 90, CB naught equals to 10. Of course, just write your units. Write your units when dealing with this problem. And you're being told, so it's symmetric here. You want about 44% conversion of reactant A. So I'm told that XA is equal to 0.44. So from these two pieces of information, I can get CA at the end of my reactor, which is, so if I have, it will be 0.44 multiplied by 90 is how much reacts, and then 90 minus answer, so be how much is left, right? 50. Basically, CA naught multiplied by 1 minus XA. So this is the product at the end of my reactor. Okay, so now because CA naught, so again, because CA naught plus CB naught is equal to 100, then if you do a mass balance, CA plus CB will always be 100. So if I plot my reaction rate, if I plot my R versus CA, I'm gonna get, again, this type of curve, and this type of curve is common. However, just having a look at the mass balance, you're gonna get the maximum at CA equals 50, right? And this simple math, you can verify it. Just convince yourself this is true. Because, you know, they add up to 100. So the midpoint, the maximum point will be at that concentration of CA, which is 50. Okay. So now let me translate this to minus 1 over RA versus CA, right? So I have minus 1 over RA versus CA. This will be just be the inverse of the other chart. Looks like this. Maybe a sharper curve. It doesn't plateau that much, but anyways, that's the curve. Our CA, or initial concentration of A, is at 90. So erase this guy here. And let's throw also my initial CA or CA naught. CA naught is 90, and my final CA is 50.4, which is just here, right? 50.4. And this is CA. And I want to, what's the problem asking for in this case? What flow reactor or combination of flow reactors is best in that it gives the smallest total volume of reactors needed? Okay. Okay, so for a CSTR, so we're going to basically compare a CSTR to a PFR to see which one is going to give me the lower volume. Okay, so for a CSTR, the volume will basically be the area under the curve, starting from CA naught and ending at where CAF here is. So this is the volume of a CSTR, or basically this is the tau for a CSTR, which corresponds to a volume of a CSTR. On the other hand, if I have a look at a PFR will be the area under this curve from CA naught to CAF. which is, this is the tau. PFR corresponds to a volume of that PFR. And both can achieve this conversion, the desired conversion. However, as you can see here, that the volume of a PFR will be much larger than a volume of a CSTR. So your recommendation for this problem will be, let's just use a single, we'll use a single CSTR, right? So for recommendation, use a CSTR, just a single CSTR, nothing else happening around. And this is really the solution for this problem. Okay, let's clear and let's move on to the next one. So for 10.3, repeat the above problem with just one change. We need 90% conversion of reactant A. Okay, so it's the same problem, except I have 90% conversion of A. Okay, let's write our given here. So this 3. This is problem 4. And again, we said this reaction is A plus B goes to 2B. RA or minus RA is equal to K. CA, CB. CA note is 90. CB note is 10. And in this case, XA is 0.9. So if 90% of this reacts, and I only have 10% left, so CAF will be 9, right? It's 1 minus XA 0.1 multiplied by this. So I have 9 moles of A left. Okay, and I want to determine, so again, same idea. Now I want to have a look which system is going to perform better. Okay, let's have a look at my chart here, or which combination of minus 1 over RA versus CA. And we said this is my chart. It's gonna look something like this. You know, smooth line. Give it one last try. Okay, this will be my chart. We said that the concentration, or C, at R max, concentration at the maximum reaction rate will be 50. And this is because, you know, if I plot R versus CA, I'm gonna get a peak where 50 is the maximum. And this is because CA plus CB is equal to 100, you know, and this, you know, they add up nicely to 100. That's why it's at 50. If they add up to a different number, you just take the midpoint of this number. So CA at R max is 50. Our initial, let's plot our initial concentration. CA note is 90, so 90 is somewhere here. CA note is equal to 90, and CAF is 9, which is somewhere here. CAF is equal to 9. Okay, so I want to find which reactor is gonna give me a better performance for this system. Okay, if I can, you know, if you compare them directly, and this is an interesting problem, you can do a bunch of things. Let's first of all compare them directly. So for a PFR is just the area under the curve. For a CSTR, it will be the box, right? The entire box under the curve. So for a CSTR, it will be box both over and under the curve, you know. This will be how we do it for a CSTR. However, in this type of scenario where you're really, your initial and final concentrations are on different sides of your of your maximum, what you want to do is you want to take advantage of the ideas we discussed before. And to take advantage of this, what we're going to do is we're going to operate 2 reactors in series. First one will be a CSTR, so I'm going to operate a CSTR in this region. So I'm going to operate, CSTR right here. We've discussed this in previous chapters, but just to reiterate this idea, where if I have my initial concentration and my final concentration around my maximum concentration, I'm going to use a CSTR in the region at the high concentration region, CSTR in high concentration region. And then I'm going to use a PFR in the low concentration region, right? PFR in low concentration region. And this really will have a much lower volume than if I just integrate the area under the curve entirely, if I only use a PFR, or if I take just one big box from here to here for a CSTR, right? And as you can see that, of course, if you run a PFR in absolute terms, a PFR is better than a CSTR. However, a combination of a PFR and a CSTR is better than a PFR alone, right? So if I look here, so this PFR in low concentration region, CSTR in high concentration region, and this will be my lowest volume. So my lowest possible volume will be, I'm going to use a CSTR from CA to CR max, and then a PFR here. So I'm going to use a CSTR first, followed by a PFR second. CSTR, PFR, this is the best option here. And again, you should always remember that if you just only have one reactor you want to use, a PFR will be better than a CSTR, because a PFR will only use the area under the curve. A CSTR will take this entire box. So the volume of a PFR is much lower. All right, so this is problem number 4. Thank you. Let me just pause for a second. Okay, let's continue the homework. We're now looking at problem number 5. And in this problem, what we're doing is, it's 10:15 from Levenspiel. You're being told we want to produce R from A in a batch reactor with a runtime no greater than 2 hours and at a temperature somewhere between 5 and 90 degrees Celsius. Okay, so batch reactor, your A goes to R, your runtime is 2 hours, and you want to operate between 5 and 90. The kinetics of this liquid first order reaction system is as follows. So A goes to R goes to S. I want to maximize air, or K1 has this expression, K2 has this expression. Determine the optimum temperature to give CR max and runtime to use, and the runtime required, and the corresponding conversion from A to R. Okay, so this is a system of reactions in series. If you recall, this was part of your exam, right? To get the equations for CR max and tau, we need to use specific equations. However, first of all, we need to determine our optimum operating temperature. So let's go to the whiteboard here. I think this has been saved. Let me clear this guy. And let's have a look here. So now we are doing problem 5, right? So this is problem 5. I don't know, maybe page 5. Anyways, so you're being told I have a system A goes to R, goes to S. This is K1, this is K2. K1 is equal to 30 e to the minus 20,000 over RT. K1 is 30 e to the minus 20,000 over RT. K2 is equal to 1.9 e to the minus 15,000 over RT. K2 is 1.9 e to the minus 15,000 over RT. And you're being told that R is 8.314. This is your standard units. It's in Kelvin, so just be careful that we need to convert everything in Kelvin, right? Joule per mole Kelvin. Joule per mole Kelvin. You're being told that your runtime should be less than or equal to 2 hours, and your temperature should be somewhere between 5 to 90 degrees Celsius. Okay, so now I want to maximize R, right? If you recall from our slides, let's go back to our slides and look at the rules of reactor design, which we talked about. It was rule number 6, right? A high temperature, let me share my slides. We said a high temperature favors the reaction with the larger activation energy, and a low temperature favors the reaction with the lower activation energy, right? So the gauge here is to have a look at the activation energies, right? If I operate at a high temperature, I'm going to favor the higher activation energy reaction. If I operate at a lower temperature, I'm going to favor the lower activation energy reaction. So let's go back here. Let's have a look. So we said high T, high temperature, favors higher activation energy, and low temperature favors lower activation energy. So I want K1, so I want K1 over K2. This is what I'm looking for. So E1 in this case is minus or 20,000. This is minus E1. So the form is K is equal to K naught E to the minus E over RT, right? So K E1 is 20,000 versus E2 15,000. If I want to favor the reaction with the higher activation energy, I need to operate at higher temperature. Okay. So in order to favor the reaction with the higher activation energy, you need to operate at the higher temperature. You're being told your temperature range is between 50 to 90, so I'm going to operate at my maximum possible temperature, which is 90 degrees Celsius, and 90 degrees Celsius corresponds to what? Plus 273, 363 Kelvin. So I'm going to operate at 363 Kelvin. Okay, so you're being told determine the optimum temperature and runtime to use. Okay, so this will be my optimum temperature, equals 363 Kelvin, and then runtime and CR max. If you recall from our previous slides, we said that the tau optimum for a PFR or a PFR or IBR, right? The tau optimum for a PFR, which will be the time for a batch reactor. So this is for a plug flow reactor, space time for a batch reactor. It's time, the time we said the equation is, no, the optimum time is ln K2 over K1 divided by K2 minus K1. And we said CR max over CA naught is K1 over K2 to the power K2 minus K2 minus K1. So I'm going to use these two equations at a temperature of 363 to evaluate my optimum time and my highest ratio of CR max to CA naught. Okay. So at 363, I'm gonna plug in the numbers here. So at temperature is equal to 363 Kelvin. If I plug in the numbers, I'm gonna get K1 to be equal to 0.397. You can verify these numbers, and K2 to be equal to 0.0132. These are all, that's minus one, minutes minus one. I have K1 and K2. I'm gonna use these numbers, plug them into over there in these two equations. So if I plug them here, I'm gonna get T to be equal to around 41.6 minutes. And I'm gonna get CR max over CA naught to be equal, and this number here will be equal to 0.58, right? So this is my temperature. This is my optimum operating temperature. This is my optimum operating time, 41.6 minutes, and this is less than 2 hours. And this is my maximum ratio of CR max to CA naught, and then you can use this to get your conversion of A and conversion of R as well, right? So corresponding conversion of A and R, at the maximum conversion, you can just do a mass balance and get it. Or if you can't do it, we can discuss it in our review session before the final. But yeah, this type of problem might show up on your final. It's sort of a simple problem where you're given some limits and you want to use them to try and solve your design prompt. Okay, let me save the screen. Let's clear all the drawings here. Let's go back to the homework. And let's continue. So problem 6, read examples 11.1, 11.4. Yeah, read these examples. They give you an insight into the non-ideal scenarios, and it's good to just, get a good idea of what's going on when it comes to non-ideality. Okay, now let's have a look at problem 7 here. Problem 7, you're being told a pulse input to a vessel gives the result shown in P11.1. So I have a pulse tracer input, and this is the concentration of the pulse versus time. Part A, you're being told check the material balance with the tracer curve to see whether the results are consistent. If the results are consistent, determine the average time, the volume, and sketch the experimental curve. So this is a typical problem where you put in a pulse to your reactor and you have a look at the pulse chart and you want to compare these two guys. Okay, so what are we comparing here? We want to compare the mass balance. Mass balance basically means I want to compare, I want to compare how much tracer goes in and how much tracer leaves over time. So how much tracer did I put in my system? M is equal to 1 mole at time equals 0 and volume is 4 liters per minute, right? So I put in 1 mole of tracer and I got out a concentration versus time curve. And I just want to compare, see, does this add up to 1 mole or not? This is really what we're doing. So let's go to the whiteboard here. And it's probably 6 now. This is problem 7. You're being told that you put in a tracer signal into your reactor, into your CSTR, right? Let's say it's a CSTR. And the conditions for this tracer were 1 mole, so M, number of moles, and you can use whichever notation you want, 1 mole. And the volumetric flow rate was for, is it liters? Or, yeah, liters per minute, right? Liters. So I just impulsed 1 mole at a flow rate of 4 liters per minute. And then I traced its presence, and this is concentration. This concentration is in moles per liter. So this concentration here, mole per liter. And our maximum concentration is 0.05. And this is time 5 minutes. So I want to compare these two. Basically, I want to do mass balance. And the approach to do this is to, the only information I have, which is close to a mass balance from the chart here, is the area under the curve. So the area under the, I guess curve or area under the chart, which let's call it curve, it's consistent. So the area under the curve on this side is equal to, 0.05 multiplied by 5, and this is 0.25, what are the units? Moles per minute per liter, right? So it's just moles per liter multiplied by minute. Okay, so this is the area under the curve, and this number should match a similar number I get from here. Since you can't really get an absolute mass balance in terms of just moles or meter cubed or whatever, we need to compare these parameters. First one is the area under the curve. This is the approach to deal with these problems. Area under the curve here, and here I'm gonna get my area, or the area of this tracer, or the area of this impulse signal. I'm not sure if you took this in controls, but the area under this signal, the equation you use is M over V, right? Just the absolute value divided by the overall flow rate, right? And this will be 1 mole divided by 4 liters per minute, and this will be 0.25 moles per liter per minute. And this is the approach to do it. This is sort of like a supplement to the lecture, and this is how you approach these types of problems when solving or when checking your tracer. These two values are equal, right? 0.25, 0.25. So this means that the mass balance are okay. Mass balance is okay, and results are consistent. So once they are consistent, you're asked to calculate three parameters. First one is the average time, the volume of the reactor, and the experimental curve. Okay, so your average time, T average, is you can just have a look at your chart and get your average time, right? It's a nice rectangle. So your average time will be halfway through it. It's 2.5 minutes. And then your volume of your reactor will be your volumetric flow rate multiplied by the time, which is 4, multiplied by 2.5. This is minutes. This is liters per minute. This is 10 liters. Okay. So this is how you get these types of parameters. And then in order to get the E, or the experimental value of the curve, or the experimental curve, in order to get the experimental curve, all you need to do is use this equation. We haven't presented this equation in the slides. It's not really part of you won't be tested on it, but it's good to know it. E is equal to C over M divided by V, right? And this is how you get the relationship between your experimental curve and your concentration curve. M over V is 1 over 4, as we said. So C over 1 over 4 will be 4C. So the value for E is equal to 4 times the value for C. So I'm going to get the same exact chart, 5 minutes, except if I put E here, I'm going to get 0.05 multiplied by 4, right? So this X is just going to be multiplied by 4. And this is how you deal with these types of problems. It's a very simple calculation. If read the examples in chapter 11, they will probably cover these in more details, talk about some more sort of thorough calculations on how to tackle these types of problems, but simple case is shown here. Okay, let me save this page, let me clear all my drawings, and now let's go back to the homework and have a look at the final problem. Okay, final problem. It's 11.3 from Levenspiel. Pulse to a vessel gives the results shown in figure 11.3. So I have a pulse into my vessel. Pulse is 4 centimeter cubed per second, and I put in 60 centimeter cubed of this tracer at this flow rate, right? And I track it at the output of my reactor, and I get this triangle shape. Now we're being told, are the results consistent? Does this match this? If they're consistent, determine the amount of tracer introduced, M, and the E curve. So first of all, we need to check, are these two results consistent? And the way we're doing it, we're going to do a mass balance. So I want to see if this actually represents 60 centimeter cubed. And you can do a mass balance either using the volume or using your space-time, as we discussed before. Your space-time is corresponds to a volume. Okay, let's write which problem is this. Problem 8. And I add a tracer. I just basically put in 60 centimeter cubed of tracer volume at a flow rate of, what was it, 4 centimeter cubed per second. The volume of volumetric flow rate of 4 centimeter cubed per second, and I get a chart which looks like this. It's a rectangle, right? Let's try to draw this rectangle properly. Anyways, it's a rectangle. It's 16, 19, 25. So this is 16. This point is 19. This point is 25. And this is a plot of what versus what. This is a plot of time versus concentration. So I have concentration versus time. Okay, so I need to compare these, see if they give me the same mass balance. I don't have any values for the concentration, so I can't really get a volume. So if I cannot compare the volume, next best thing is I'm going to compare my space times or my, my actual residence time or my space time. So let's try to get this. So in order to do material balance by comparing the residence times, because I cannot get any information for the volume, there is no concentration given here. So let's try and do it. So for this guy on the right here, we said that tau is equal to, or maybe, tau average or time average is equal to 60 divided by, it's 60 centimeter cubed. It's, is equal to V over V. We've discussed this before. Centimeter cubed over second, and this is 15 seconds. Okay, this is what's actually been pumped into the system. This is the tracer numbers. Okay, let's have a look at what we get from this chart. So I need to get the tau average from this chart. It's the average time from this chart. It's basically the point at which I have this point at which areas on both sides are equal, right? It's the point at which the areas on both sides of this curve is equal. And here you have to use some of your, I don't know, SAT geometry, I guess. So what's the area of this triangle if I'm not given a height? It will be, what will it be? It will be a point that's 2/3 from here, right? Multiplied by the height of this rectangle, right? So this rectangle right here, this rectangle is equivalent to the area to this triangle. So it will be, let's see, it will be 16 minus 19 is what? 3. 3 multiplied by 2/3, or 2/3 between 16 and 19, which is what? 18. So 3 multiplied by 18, plus on this side, same idea. The area of this triangle right here is equal to a rectangle that is 2/3, or 2/3 from, or 1/3 from the top, basically 1/3 from the top here, 2/3 from your bottom of your rectangle. So here 1/3 from the top, 19 to 25, that's 6. 1/3 is 2. 19 plus 2 is 21 multiplied by 6, right? So this is the overall area of the area of rectangle, and then I'm going to get the average by just dividing by the overall scope or overall time. 25 minus 16, which is 9, and this will give me the time here. If it was a nice cute rectangle, it will be the half point, because the area here is equal to the area here. If it was a nice triangle, it will be just the midpoint, because the area here is equal to the area here. But this is sort of a slanted triangle, or one side of the triangle is bigger. So this is how you do the basic geometry stuff to get the midpoint. Okay, just remember how to do it. You can revise how to do it, but it's not gonna. It's either a rectangle, a nice triangle, or a strange triangle. You're not gonna get a rhombus or something, right? That's it. Anyway, so if I do these calculations, I'm gonna get 3 times 18, that's 54. 21 plus 6 is 86 divided by 9. Should get something around 20, right? 54 plus 86 divided by 9 is 20. Let me just verify this using my calculator. Where did this guy go? Oh, here it is. Okay, 3 times 18, 54, plus 21 times 6. Actually, 21 times 6 is 126. Yeah, 126 plus 54 is 180 divided by 9. That's 20. So this will be 20 seconds. Okay. So you see this is different than this. So results are not consistent. And there's something wrong with your system. You need to take a closer look at this reactor. Is it leaking? Is something going on? Is my cooling jacket, you have a phase change in the cooling jacket? What's happening here? Why don't they make sense? Why is the mass balance not closing? Okay, so this is the end of this homework. Please try to, this homework is sort of supplemental to the lecture, introducing some new techniques on how to solve some of these problems. Try to do it. If you have any issues, please come to office hours and we can go through them together, or send me an email. We can always communicate by email. Thank you very much.